right, good evening, everybody. It's basically 7:30, so let's get started. I'm David, and this is another episode of A Thousand Shimmering Lights, which I normally say is the only YouTube planetarium show where you get to be the planetarium director by deciding what we talk about with your questions and topics. But like last episode, that's going to stay in, this is live. Like last episode, um, this episode actually has a theme, and this theme basically occurred to me immediately after I did the last episode, and that is astronomy in color. And I'll talk a little bit more about that in a second, but first, let me do a little bit of housekeeping. Hey, what's up? Max Ravenhood is here, or Max Ravenwood, so I already have one viewer. If you are viewing the channel, please say hi in the chat, even if you just are just saying hi. That helps me feel like there's somebody out there actually listening to me and I'm not just talking to my wall. While I give some time for more people to start to join the stream, because they are all going to start showing up now that it's officially 7:30, I'm going to do a little bit of the usual housekeeping I do at the start of any episode, and that is to talk a little bit about the Astronomy Club. So, Max, if you're joining us from Jacksonville, cool. If not, then this may not be as applicable to you, but I am actually on the board of directors for the Northeast Florida Astronomical Society, and we are the astronomy club here in Jacksonville. So if you live in the greater Jacksonville area and you are interested in astronomy, check us out. Our website is nefas.org. That is NEFAS.org for Northeast Florida Astronomical Society. We do have memberships. They are annual memberships, and that is to be found here under memberships. Join NEFAS. You can see all about that. I'm going to quickly go over our calendar of upcoming events. So let that load for a second. So tonight, of course, is the 15th, and it is the third Thursday of the month, which is why I'm doing this. I do this every third Thursday of the month. We had our board of directors meeting on Monday. But coming up this weekend, we have a dark sky observing session this weekend and next weekend. We plan those for the Saturdays closest to last quarter and new moon. So you see here last quarter and new moon right there on the calendar. That is so that we don't have a moon in the sky when we do these observing sessions, because the whole point of these is to get out under a dark sky. These are not outreach events like the ones we do at Hanna Park that I'll talk about in a second. Tucson, Arizona. Wow. Okay, so yeah, I do apologize. Please bear with me while I go over our events calendar for a second for the Jacksonville Club, but that I will dive into stuff that's applicable no matter where you live. So anyway, we do have our dark sky sessions. These are not outreach sessions like I was saying. These are where our club, we get out somewhere dark and we do our own observing. That's not to say that they're not open to the public. They very much are. Anyone's welcome to come out there and join us. Just keep in mind that it's not outreach, so we're not going to be necessarily all set up, for you to view and everything. A lot of our club members will be doing their own observations, although usually people are very friendly and will say, hey, come take a look, I got the Whirlpool Galaxy or whatever. But that's not the main purpose. The main purpose of these is this is the thing we do for ourselves. That said, it is a dark location. It is out in the middle of nowhere. And if you've never seen the Milky Way or gotten out under a truly dark sky, it is an excellent time, and you should consider coming out there with us. If it is your first time coming out, I recommend meeting up with us at the Firehouse Subs at around 6:30, and then following somebody out to the site. If you're a club member of NEFAS, I like to send out emails letting people know exactly what the plans are, or you can check out our Facebook page. And then real fast, I'll just talk a little bit about what's coming up in October. The big thing is October 1st. So this is our Hanna Park stargazing session. This is our outreach session that we do. And this is meant for people to come. We're going to have a bunch of telescopes set up. I do a laser pointer show where I talk about what's in the sky, show people constellations, that kind of thing. It's always a wonderful time. And this time is especially cool because it's International Observe the Moon Night. So we are really promoting this event. We're really going to try and go all out on this one. And it's going to be one of our biggest events, probably the biggest event we're going to have for the rest of the year. So I sincerely hope you can make it if you live in the Jacksonville area, and check that out. The park charges $5 to get in. We don't charge anything. The gates close. Depending on daylight savings time, it fluctuates. But for this event, I think it's still going to be 7:30 is the cutoff time. So you have to be in by then, and then you just hang out with us while we wait for the sun to go down. But if you do have like a new telescope or something and you want to learn more about it, that's when it's very useful to show up early because if you get there nice and early, we can help you with that while we wait for it to get dark. So I always recommend, even if you feel like, oh, I don't want to bring my telescope, I don't really know what I'm doing, and there's going to be people there like setting up the scope, so we'll just use theirs. Bring yours because that's how you learn to use it. You bring it and we teach you. And then on the 13th of October is going to be my next live stream, so that's where I'm going to stop for now, and I'll talk about the rest of this stuff next month. So let me see if anyone was patient enough to stick with me while I did all that house cleaning. Vinny, hello, what's up? Okay, we got 5 people viewing. Excellent. Okay, so with all that stuff about the Astronomy Club out of the way, let's talk about tonight's topic. So typically I don't have a topic. Usually I just let viewer questions drive the discussion. And tonight I'm going to try and leave a lot of room for viewer questions. So if you're watching the stream and you have a question about something, whatever, just throw that right in the chat. I like the chat to be very active and for this to feel casual and like a conversation. So to start off, one thing I like to do once I've gone over the calendar is I talk a little bit about what's in the sky tonight. So since we have viewers from across the United States, I don't know what your time zone is and what time it is where you are, but this is going to be the sky tonight. And this is free software that I use called Stellarium Web. It allows me to show the night sky, pull up the constellations, the whole thing. It's basically planetarium software, and it's completely free and browser-based. You can literally just Google Stellarium Web and play with this yourself. And so it also allows me to time travel if I want to go to different times of the year, but this is what the sky should look like tonight. So some things to point out. If you get out your telescope tonight, for one thing, if you look to the east, you should be able to see Jupiter. Jupiter has been approaching opposition. If it hasn't already hit opposition, I think it's going to soon. And it's really cool to see through a telescope if you never have before, and it's very easy. The way to find it, let me see what constellations are nearby. So there's not a whole lot of bright stars nearby, and that's going to be an advantage because Jupiter will clearly outshine anything in the eastern sky. So if you get outside and you look east, the really bright star, that's your guy. Point your telescope at it. It's going to be really easy to find. Also, we are finally getting late enough in the year where the Andromeda Galaxy is going to start to become available again. And again, for a new astronomer, a new amateur who wants to get into deep sky and start looking at things outside the solar system, the Andromeda Galaxy is a great target. The best way to find it is you're going to look sort of northeast-ish. If we look here between north and east, it's almost halfway. We find this big W shape. One thing about this software is that the size of the dots corresponds to the brightness of the stars. Oh, Max, welcome back. Yeah, you missed some of the housekeeping, so you're good. But the size of the dots in this software correspond to the brightness of the stars. So you'll notice that Cassiopeia has a bunch of big dots, so it's a bunch of bright stars. I've shown Cassiopeia to people in downtown Jacksonville, right? It's not a very dim constellation. It cuts right through light pollution. In fact, it may be a little easier to find in light polluted conditions because, as you see, it does lie along the Milky Way. So a little bit of light pollution will actually help it contrast more because it's going to cut out some of the distraction if you're just learning to find it for the first time. This surprises people, but I often tell people start trying to find constellations in a light polluted sky, and you'll easily learn to recognize the brighter ones, and then they'll help you when you have a dark enough sky to find the others. But once you found Cassiopeia, once you found this big, it'll either be a W or an M, depending on where it is. Right now, it's sort of like a W. When you find it, you'll notice that one leg of the W is all sort of stretched out and short, and the other one is bunched up and tall, right? And what you're going to do is you're going to take the bunched up and tall one and shoot through it like an arrow through a bow, right? And you will hit this reddish star here named Mirac. And we're going to talk tonight about what it means when a star is red, right? That's part of the topic, astronomy and color. We're going to talk about what the meaning is of different colors of stars. But once you've found Mirac, you're going to jump a couple of decently bright. These may be a challenge under light polluted skies, but they're fairly bright, and you can usually get both of them if you look carefully. But you're going to jump 2 stars back, right, towards where you came from. And right here, if you point your telescope at this star and just sort of look nearby, that's where M31 is, also called the Andromeda Galaxy. It's our nearest neighboring galaxy, and it is only about 2.5 million light years away. And it is big enough that if you get somewhere dark enough, you can just see it with your unaided eye. Those dark sky sessions I mentioned before, we routinely will just go, there it is. But under a more light polluted sky, your telescope will easily get the core of the galaxy, and you'll see a big spherical smudge. And if you get out somewhere dark, you'll get the elongated shape of the disk, because Andromeda is a tilted disk, not quite edge on, not quite face on, sort of halfway between the two. Speaking of that, we'll talk a little bit about some of the constellations we can see. The Great Square of Pegasus is sort of nearby. So we've got Jupiter on one side, which is not always a guide for you. That will move about. But we've got Cassiopeia on this side. And this, it doesn't look that big in the software, but this square takes up some real estate, right? It will look huge in the sky. And then from there, you can find the rest of Pegasus, again, if you're consulting your charts. We have Aquarius nearby, but it's a bit of a challenge, I'll be honest. Saturn is also in the sky tonight, and if you found Saturn, it's right here in Capricornus. Now, as we all know, when Saturn is located in Capricornus, it signifies absolutely nothing, because the stars and planets have no impact on your life, other than being awesome. But here it is right here in Capricornus, and again, it'll be just a really bright star. It'll be about half the brightness of Jupiter. And that's because Saturn is a little bit smaller than Jupiter, but it's also about twice as far away. So it looks about half as bright, right? But the cool thing about Saturn, and the thing that blows a lot of people's minds who have never seen Saturn through a telescope, is just how little of a telescope you can have and see the rings. People are always shocked when I show them Saturn. They say, oh my goodness, I can see the rings. It looks like a picture. And they can't believe it. They're like, it looks fake. But then I have them look down my telescope, and it's just a hollow tube with a mirror. There's no way I could fake it. But Saturn just really is a very impressive object. It's a really cool one to show your friends, and you will see the rings. Some things to look out for with Saturn. Check how tilted it is, right? Check if you can see the planet casting a shadow on the rings behind it, or tilted the other way. See the rings casting a shadow on the planet. Those are all things to look for. As Saturn goes through its orbit, which takes a very long time, but we catch up to it every year, you'll see variation from year to year. If we look to the south, we'll see Sagittarius and Scorpius. Now, these two constellations are probably some of the easier ones to find. You'll see they're kind of low on the horizon right now in the software, and if I time travel forward, they are going to set immediately. These constellations are more so associated with summertime, and as we move into fall and into the winter, those constellations are going to go away and be replaced by some wintertime constellations, which we can talk about if you guys are interested in that topic. So the best way to find Sagittarius is just to look south and find the brightest stars. If I delete the lines real fast, you'll see that these dots stand out against the background. They are very, very bright. And again, downtown Jacksonville, no problem spotting Sagittarius. But you will also notice it is right up against the loudest part of the Milky Way, which is in fact the core of our galaxy is in this direction. So again, a light polluted sky is actually going to make it a little easier to spot the first few times you do. One thing to look for when you're looking at Sagittarius is you're going to find that the bright stars form this very unmistakable teapot shape, right? So we have this sort of quadrangle here is like the kettle, the spout comes out this way. We've even got a handle over here, and we even have a lid coming up, right? With Caus Borealis being like how you'd open the lid of this teapot. But the constellation Sagittarius itself does actually include additional stars. Nearby is Scorpius, and my favorite way to find Scorpius, if I delete the lines real fast, first of all, as you can see, Antares, very big dot, very bright star. It's also a reddish color. Again, we'll talk a little bit about that later. One thing you'll notice about Antares is next to it are Tau Scorpii and Alniot, and they form a very slight bend like this. Then over here, we've got Acrab, Deshuba, and Pi Scorpii. Those almost form like a second slightly bent line like this. So I tend to look south, and I look for that pattern, right? And if I find Sagittarius, I'd look at where the teapot is pointing, and I start looking in that direction. Once you've found that, that's sort of the body of the scorpion. And then what you're going to do is you're going to take the curve of Antares, Alniot, and Tau Scorpii and just keep it going and hit every bright star that you see. Epsilon Scorpii, Mu Scorpii, whatever's happening down here. This guy, Sargas, over to here. Kappa Scorpii, Shaula, and there's an NGC right next to this star. That's not the proper label. G Scorpii, right? So you're going to get this sort of, it comes down, around, and then a sharp bend right here. And that, of course, is the stinger. That's the tail and stinger of the scorpion. So that's Scorpius. If you look to the north, you can find the circumpolar constellations. These are always available. Circumpolar constellations are so called because they are around the pole, right? The easiest circumpolar constellation to find is Ursa Major. And part of Ursa Major is the Big Dipper, and that's the easy part, right? So already you can see where I'm talking. You see these big bright guys. They are all outrageously bright stars. Here's a little fun thing for you if you've never checked this out on the Big Dipper. This star right here, Mizar in the handle, there's actually two stars there. And if you look closely, you can see them with your naked eye. You can actually see a pair. Some people find it a little easier than others. Of course, everyone's eyesight's a little different. And in ancient times, I've been told that was used as an eyesight test. Could you see both of those? It was like a way that you could gauge how good somebody's eyesight was. If you find this Big Dipper asterism, an asterism is a pattern of stars that is not itself a constellation. This asterism is part of a constellation called Ursa Major, the Big Bear. Once you find it, if you go to the edge of the bowl, Merak to Dubhe, and you keep going, you will hit Polaris, and you will be surprised because a lot of people think that Polaris is the brightest star in the sky. It's a very common misconception, but in fact, Polaris is only the 43rd brightest. Still a fairly bright star, still stands out, but not nearly as bright as some of the others. And so a lot of people are sometimes surprised to see how dim, relatively dim, Polaris is. Once you've found Polaris, you can go sort of towards the tail of Ursa Major direction, and you'll hit Kokab and Farkad. Those are the only other two bright stars in this constellation. The rest of Ursa Minor, or the Little Dipper, or the Little Bear, is somewhat faint. So you'll see these two stars, and then the handle coming out this way forms the rest of the Dipper. But those are often difficult to see. All right. And can we do Scorpius again with the lines in place? Yes. Okay, I'll do that. Like I said, this is your show. Feel free to always drop a question, and I'm going to try to answer your questions. So this is Scorpius with the lines included. Now, the person who drew these lines drew them a little differently than I might have. And there is no like official way to draw the lines. Funny enough, the constellation is the stars, and then different people have different opinions on where to draw the lines. I like to do an arc here and an arc here because that's just what I notice in the sky. And I just sort of imagine a blob around it to form the body of the scorpion. And then I just sort of mentally add his pincers up here. There's not really stars for them. You got to use your imagination. But then coming down from here, you'll see this sort of big curvy loop of bright stars forming the tail. And then this person has not chosen to include G Scorpii, but actually I always like to include it because to me that just completes it for me. I got the nice thing and then boom, a stinger. It couldn't be more perfect for a scorpion. So that's how I imagine Scorpius. So thank you very much for the question. Let me just zoom out and swing around a little bit and see. I'll show you guys a couple more things, I guess. I want to save some time tonight to talk about our main topic, which is going to be astronomy in color. So there's one more thing I'll show you. Off of the Big Dipper, if you follow the curve of the tail, you will arc to Arcturus, which helps you find the constellation Boötes. And then you can spike onto Spica, but Spica is actually not in the sky right now, and won't be until next year, because you see it's already set. So we get new things from the east, and things leave in the west, and that's just the way it is. That's an interesting constellation. What do I have my location set to? Who knows? It says near Jacksonville. I've never seen this constellation. It's low. It'd probably be blocked by trees, but I'm gonna have to check it out sometime. All right. So let's get into tonight's topic a little bit: astronomy in color. So first off, I want to talk about what color actually is, and for that, I'm going to bring up my visuals. And I always use Wikimedia Commons when I can for visuals because I don't want to get copyright striked. This channel isn't monetized at all, though, so I'm not actually making money off of anybody's images, but nonetheless, want to try and play it safe. Pull up the electromagnetic spectrum. Okay. All right. Got to stay hydrated. It's very important. All right. So this is the visual electromagnetic spectrum of light. What does that mean? Well, light is a wave, but it's also a particle. And I am not getting into quantum physics tonight. But basically, for our purposes tonight, we really only care about the wave aspect of it for the most part. But basically, it's a wave of electromagnetic energy that travels through space at the speed of light, of course. If I bring up the electromagnetic spectrum, the different kinds of light are determined by the wavelength, which is to say that regular pulse that a wave does, the faster it goes, the closer those waves are to each other, the more bunched up they are, the shorter the wavelength, and the slower, the more stretched out they are. And actually, I think there's some pictures that show that a little bit more clearly. This picture is a decent one. Right, so this is the electromagnetic spectrum. And you see there's a stretched out sort of long waves are over on this side of the chart, and the bunched up short waves are on this side of the chart. But I'm going to grab this chart because it helps to illustrate an important thing about the electromagnetic spectrum, which is the longer the wavelengths, the closer to the red, the shorter, the closer to the violet, the blue, and the violet. But most of the electromagnetic spectrum is invisible to our eyes. So most of the light that exists, you don't actually perceive it as light. You can't see it, right? Even though it is technically a form of light, it's light that's invisible to your eyes. Only this narrow section of the entire spectrum is visible. And all the colors we can see lie within that part of the spectrum. So one possible way to think about light is you can imagine that there's colors that we cannot see because they lie outside of this spectrum. But another way to think of it is there are not colors that we cannot see. And that is because color is a label that our brain applies to light. So basically, when you see light, wavelengths of light enter your eye, and different wavelengths of light will activate different cone cells on your retina. These cone cells are sensitive to different parts of the electromagnetic spectrum, and the amounts to which those cone cells are activated to varying degrees gives your brain a signal, and your brain assigns that a color. Some people actually have something called synesthesia where they can assign color, their brains will assign a color association to things that are not even light. So some people listen to music, or when they read written words, there's a color association in their brain because the part of the brain that processes color has crossed over with the language center or the auditory center and that kind of thing, and is reusing those labels for other things. Um, it's like I said, it's called synesthesia. You can look it up. I actually am synesthetic, and and for me, it's the letters becoming colors thing. Uh, Matt says, "Is Jupiter really that big? It won't appear that big in the sky. So in the software, the size of the dot correlates to its brightness. So it was showing a really really big dot to indicate that it's very very bright. To your eye, it will look like a pinpoint like every other star. But if you get it in a telescope, it will be nice and big. So that's a good question as well. So with that being said, when I talk about astronomy and color, I'm mostly talking about the spectrum of electromagnetic radiation. And yeah, since this is the only kind of radiation our eyes can detect, it's the only kind of radiation that our brain assigns colors, right? So, what can this tell us about the objects that we're looking at? Well, I made myself a little list of topics that fall within tonight's thing. So let's talk about some of those. And I've hinted at one a couple of times, so we'll start with it. And actually, you know what I'm going to do? I think I might show you guys the image so that if something catches your eye and sounds interesting, we can talk about it. Um, let's see here. So this is my list that I kind of came up with for. Hold on. Is it Alt that I had to click? I forget the button to let me resize without resizing the image. But anyway, this is my list for tonight of topics that have to do with color and astronomy. Don't think I'm going to be able to cover them all, so I'll put this up every so often if you guys have, so you guys can take a look and let me know if there's anything on that list that sounds interesting to you. But let's start with stellar evolution because I hinted at that a couple of times. So I said that there's a couple of stars that are red, and what does it mean when stars are red, right? So stars do not exhibit the full spectrum of color. You will never see a green star. You will never see a purple star, right? You will usually only see shades of red, white, yellowish white, bluish white, right? That's the sort of spectrum. So if you imagine a spectrum that goes red through yellow through white to blue, that's kind of what we're looking at. And I will bring up, actually, let me bring up Hertzsprung Russell diagram. Did I spell that correctly? Did I mean that? Yes, I sure did. Okay, so this diagram is a bit complex. There's a lot going on here, and we can dive into it a little bit. And oh my goodness, and this one isn't even in English. But the main thing I want you guys to see is that the left to right axis on this diagram is color, right? And so you'll see these are all the colors that stars can be. So you won't see purple, you won't see green, right? So the question is, why is that the case, right? Somebody asked me one time, are there any purple stars, right? Why? Why are there no purple stars? Well, the reason is because stars don't just emit one wavelength of light, right? So if a star just emitted the wavelength of light associated with green, it would look green. But what stars do is they basically put out the whole spectrum. And in fact, they're even putting out things like X-rays, radio waves, the ones that we don't even see. So a star's overall color is going to come from a blend of all those wavelengths, right? And when you blend all the wavelengths together, you get white. But if that blend of wavelengths is slid over to the red or the blue, it's more dominant in the red or more dominant in the blue, right? So there just are more blue wavelengths than all the others. Then when it mixes, there's still going to be an overabundance of blue and it's going to look bluer. Whereas if it's towards the red end of the spectrum, that's going to make it look redder. But if that overabundance is sort of in the middle, it's going to turn white, right? So that's why we only get stars in these colors, blue through red. But one thing that the color can tell us is the temperature of the star. Because this axis left to right is not just the color axis, it's also the temperature axis, right? The hotter a star is, the bluer it is. And the cooler a star is, by star standards, you'd still incinerate, but the cooler it is for a star, the redder it is, right? So that tells us a lot about the star. When we look at just the color of a star, we can tell the temperature of the star. Max says, since I brought it up, why is Mars red? Excellent. I will pin that one real fast and talk a little bit more about the star color, and I'm going to circle back around, and that'll be our next one that we cover since you asked. So why is Mars red? Putting a pin in it now. So the star color relates to its temperature. So what can the temperature tell us about the star? Well, typically a star's temperature is based on its mass. The bigger a star is, the heavier it is, the more its own weight is crushing on it, and the pressure of its weight heats it up. So the blue stars tend to be really big. But there's a bit of an exception to that rule. So basically stars, there are these really little red ones that we call red dwarfs. They're very small. They're red because they burn very cool. Then there are the blue giants, right? There are these big blue stars. There are also blue main sequence stars and all kinds of stars. Like I said, this chart gets kind of complicated. But generally speaking, blue stars are just really big, high mass stars. The other thing that the temperature of the star will tell us is that the star it can give us a hint about the age of the star, because blue stars only last so long, right? Big stars burn so hotly that they burn through their fuel quickly, undergo core collapse, detonate, and then just die, right? So if you see blue stars, those stars can't be that old. They don't last that long. And so when we look at, and we're going to talk about this in a second with galaxies, you can gauge the age of a cluster of stars or a galaxy by its color. Because the bluer it is, or the more blue stars you see, then that means that new stars are being made, right? Because the blue stars have to be recycled, right? If new stars aren't being made, the blue ones all die off, and the galaxy turns an amber color because all that's left are white, yellow, and red stars, right? So we'll show some pictures of that in a second. Actually, I'll show some pictures of that now. So it happens to be that a lot of the spiral galaxies are blue, right? So if I pull up Triangulum Galaxy, this is a good example of one. All right, you see how it's got this blue color. So what that tells us is this galaxy is making new stars, right? If it wasn't, it wouldn't be blue, right? All the blue stars would die off, and we would just be seeing, yellow, red, orange, that kind of thing. The blue stars indicate the presence of new star formation in that galaxy. And if we can compare it to something, we can do Messier 83. 83. And, sorry, wrong one. I always get them flipped around. 85. Is it 85 that I want to look at? It's at 87? I know it's 87. That's the one I want to look at. First of all, that's where they got the picture of the first ever black hole. But you see this sort of amber haze, almost like a street light in fog, right? We're not seeing, other than this streak coming out, which is actually exciting gas and making the gas glow blue. And that's the result of that black hole. Otherwise, we are just seeing a lot of amber color. And so that tells us that this galaxy is not making new stars, and all the big hot blue stars died off. But the other thing that a star's color can tell us is that red stars, which are not red dwarfs, so larger red stars, are dying. And I'll explain how we know that. So basically, I mentioned that the stars turn red if they are cooler. One thing that happens near the end of a star's life is that the core begins to collapse because it runs out of hydrogen fuel, right? So a star is always trying to implode and explode all the time, right? Its own weight is always trying to crush it, and then the nuclear fusion reaction going on inside the star is always trying to blow it up. And the equilibrium between the two determines the star's shape and size. Well, shape, it's always a sphere, determines the star's size throughout its life. But when it runs out of hydrogen fuel in the core where the fusion happens, that outward force goes away, and so the star begins to collapse internally. Stars are so big they don't all collapse together. The inside collapses and the outside is kind of slow to catch up. And what happens is when that core collapses, we have an increase of pressure and heat. That increase of pressure and heat is going to introduce a new fusion reaction. All the helium that star has been making throughout its life, because stars turn hydrogen into helium, well, now that helium, that helium is going to be turned into heavier elements, and it's going to release a lot more heat and energy. And that energy and heat are going to ripple outward and cause the star to expand. But the ideal gas law says that if you take a gas, or a plasma in this case, and expand it, all other things being the same, the temperature and pressure have to drop, right? N equals RT if you've taken a chemistry class. So when that happens, the star will rapidly cool, not in the core, but in the outer layers. And so that turns it red. And so that means that and they swell up and they get really, really big, much bigger than they were in life, even though it's the same amount of material. That's why they cool. And so that's why when stars run out of hydrogen fuel, they swell up and turn red. And that lets us know that now the star is undergoing the processes at the end of its life. It's going to do a series of core collapses, make progressively heavier elements, and then depending on the mass of the star, it's either going to explode in a supernova and produce either a neutron star or a black hole, or it's going to have the more gentle death of a sun-sized star that leads to something we call a planetary nebula, which, as anyone who watches my show knows, is my least favorite name for anything ever, because it has nothing at all to do with planets. But that's another indication that we can get from the color of a star. And now Max has been so patient, I'm going to address her question of why is Mars red? And the simple answer is rust, right? The Martian soil is rich in iron oxides, and iron oxide just means rust, right? So there is a richness of rust in the surface of Mars. And really, Mars isn't red in the sense of like a red tomato is red. It's more red like how we would say that like somebody's a redhead, like they got red hair, right? When in reality, their hair is like orange, right? Mars is kind of the same way. If I pull up a picture of Mars, here we go. It looks a little redder in some pictures than others. That has to do with the camera settings and filters being used. We're going to talk a little bit later about coloring of astronomy, images, how images are actually how color is applied to images, and so the true color of Mars. This says the true color of Mars, so maybe this is a true color image. It is this sort of orangish red color. Part of that is not unlike the orangish red color you get in many deserts here on Earth, right? If you go out to the Midwest, actually somebody, I think maybe Max or somebody said they were joining us from Arizona. If I grab a picture of the surface of Mars, I've never been to Arizona, but my understanding is it wouldn't look that out of place in terms of wide open, red, dusty desert type of environment. But the presence of those iron oxides gives us that rich orangish red color. An interesting fact about Mars is that there are these darker regions as well that result from different surface features, impactors and that kind of thing, hitting the surface of Mars and various things like that, causing there to be some variation. And I want to say that this is also where more of the solid rock is exposed versus the sand. I think the sandy part of Mars, if I'm not mistaken, is the redder bit. So excellent question, Max, about why is Mars red, and there we go. So let me consult my list of topics again. So we talked a little bit about star color and stellar evolution. Stars are born and they die and they turn red near the end of their life, and the blue stars are big. I think I'll circle back actually because I kind of want to talk a little bit more about Well, no, actually, what looks interesting to me? I'm kind of just playing around with it. We talked about galaxy color as well. Um, let's talk about false color imaging. I did bring up that topic, so let's talk about false color imaging. This is what made me want to do this show, by the way, because last time, so normally I don't have a theme, but last time when I did the James Webb themed episode, of course, because all the James Webb images came out, I mentioned during the talk false color imaging, right? And we went through a whole I think I did an episode where we talked about nebulae and did the whole thing about nebulae, and we talked about false color imaging for that as well. And it made me immediately think, oh, let's talk about color and astronomy, right? It just seemed like a cool topic, so that's why I did this. So false color imaging is something that's done in astronomy with images taken by like observatories and deep space telescopes, and there's a reason for it. It's not to just be misleading. But let me show an example of false color imaging, and then we'll talk about it. So I'm going to pull up Messier 16, also called the Eagle Nebula. Now, first, I'm going to show you this picture. This is a true color image of the Eagle Nebula. So if you just take an image of the Eagle Nebula, the color that it is, ooh boy, I'm going to let that load. Bear with me, guys. It's a big old picture. All right. So this is the Eagle Nebula in true color. This is what we would get if we just, image it as it is. And it's pink, right? You guys will notice it is quite pink. If I zoom in a little bit, oh, I done did it now. Whoo boy. All right. Here we go. This region right here, we see these three big columns that look like they're silhouetted. And these are patches of gas where the gas is a bit more dense and the stars behind are kind of illuminating it, and the glowing gas is sort of illuminating this more or less from behind and silhouetting it a bit against the background. And this part of the Eagle Nebula is famously called the Pillars of Creation, right? And we zoom out, we can see it's right here in the picture. Okay, so when I searched for the Eagle Nebula, right, go back again, immediately we saw this come up in the search results, right? This is another picture of the Pillars of Creation, but it's not pink, right? Why isn't this picture pink? Well, that's because this is not a true color image of the Pillars of Creation. This is a false color image, right? So what happens is with these telescopes like the Hubble, like the James Webb, the images they actually capture are grayscale. They are just black and white, right? What they do to make a color image is they use different filters to filter for different wavelengths of light, and they will snap a gray image, a grayscale image in that wavelength, right? So they'll put a filter on that only allows light of a particular wavelength or a set of wavelengths can get through that filter. Nothing else can, and then only that light is going to read on the digital chip, right, to record the image, and will produce a black and white image. And the telescope will take tons of these pictures. It will swap out filters, right, and take a bunch of pictures. And then later on, all those black and white pictures have a color applied later on in the computer where the white is replaced by the color that they assign, right? And so then you have a bunch of colorized images. So it'll be black and red, black and green, black and blue. Those then get stacked up digitally in the software, combined into a single image, and we get this. If they want the image to be true color, then they will assign the colors 1-to-1. So if you have a filter that's filtering for red light, you make that red. If you got a filter filtering for green light, you make that green, and then you stack it up and you get a true color image like the last one that we saw. But that's not the only option when it comes to applying colors. Now I have a page here. This is not Wikimedia Commons. This is actually the Hubble's official website. So NASA, if for some reason you're watching this, I know I didn't get permission. Please forgive me. It's for the better purpose of education, though. I think they'll be okay. And again, channel's not monetized. So here we see this idea that the whole spectrum of light can kind of come through, but if the glass is green, only green light gets through, right? So what happens is, so here we have an example using Mars where they say, well, we had a filter that captured this piece, we had a filter for this, and we had a filter for that. So these were the black and white images we got, right? Mars really is sort of a reddish color, so it looks brighter in the image taken with the red filter than in the one taken with the blue filter, right? So they took the bluish filter and they made it blue, and the greenish filter and they made it green, and the reddish filter and they made it red, like this. Then when you stack them, you get this, right? That's how you get a true color image from a bunch of black and white images. You have to use filters that will filter for certain wavelengths of light to give you that result, right? So the other thing, though, is that you see here, they pointed out that this spectrum actually goes a little bit into the infrared and a little bit into the ultraviolet. So they can actually cheat a little bit and use an ultraviolet filter but still colorize it. And that's why we can see some glow around the edges here, right? We're seeing some things that we wouldn't normally see because we actually are, in this image of Mars, it's as if our eyes could see the ultraviolet a little bit. But if I take this image, the Crab Nebula, here we get an example of false color imaging, right? They took this piece of the spectrum, which is sort of in this bluish area, but they assigned it the red color, right, to what they got. And then they took this bit that's sort of in the orangish area, but they assigned it the blue color, and so on. And so this is what we get as a result. Why? Why do that, you might be thinking? Well, the reasoning is that the image doesn't just have artistic value or aesthetic value, but it has scientific value. So the filters that are used are not just trying to capture different colors, although they in effect are, but the truth is they want to capture different chemical elements. And this brings us into the topic of spectroscopy, which is going to actually dovetail nicely when I talk about the composition of stars, which is another spectroscopy topic. Let's bring up this. Okay, so it's an interesting fact of chemistry that when you take a chemical element and you burn it under the right conditions, it will glow, or you can ionize it as a gas or a plasma, and it will glow in certain colors of the spectrum. But also, if you shine light through a particular chemical element in a gaseous form, it will absorb very specific wavelengths of light, right? So those two things are true. You ionize a chemical element, it will glow in particular, very specific wavelengths, and if it blocks light from behind it, it will block the same wavelengths that it would emit if you were making it glow, right? So if we were to invert this, we would get the emission spectrum rather than the absorption spectra. But nonetheless, you can see that there is a characteristic pattern of lines associated with every chemical element, which means that if you find a line that doesn't exist on any of the other elements and isolate it, that line is tied to that element, right? So when it comes to the emission spectrum, right, hydrogen emits in a particular part of the spectrum, helium emits in a particular part of the spectrum, etc., etc., etc. So what you can do when you are imaging an object is you can filter for the specific wavelengths that chemical element emits. So you can filter for the wavelengths associated with oxygen, and oxygen emits a particular thing when ionized in a vacuum, right? It triple ionizes, and so we call it, no, double ion, O2. Is it O2? O3, sorry. It triple ionizes, and we call it O3, not O3 like O with a 3 above it, like ozone. But in astronomy, when we say O3 or H2 or whatever, we're actually referring to how many times it's ionized, and it's a Roman numeral, so don't let that throw you off. So oxygen 3 emits in a particular part of the spectrum. It's actually sort of in this bluish patch. Hydrogen has a couple different places where it emits. There's an alpha and a beta part to hydrogen, and we can select for just hydrogen alpha, for example. We can select for sulfur 2. We can select for, nitrogen, the different chemical elements. And then rather than do a true color image, which, like that image of the Eagle Nebula I showed earlier, may just sort of all be one general color, if we assign them very contrasting colors, later, when we assign the colors to the filters, we can get a false color image that, while it doesn't look true to life of the actual color the object is, the image itself communicates something about the object composition, right? So in this particular case, I don't think they explain here. They just say it was different elements. I don't think they actually say what colors they assigned to what elements. If I'm not mistaken, I think with Hubble they liked to assign green. No, they like to assign red to hydrogen, I think it was, and then sulfur and nitrogen would tend to be assigned green, and then oxygen would tend to be assigned blue. And so that gives us an idea of the composition of this object. We see a similar thing happening here with the bubble nebula, although this one again is closer to true color because they put blue on the blue and green, and red on the red. But this one demonstrates another interesting concept, which is that here we have two of the filters are very similar. Well, if we want to know what got through this filter and what got through that filter, we need to make them more different. So even though, really these should both register as red, well, this one's partway between the two, so let's assign it green so it really stands out, and we can tell what was, hydrogen and what was the other thing. And then we get this image of the bubble nebula. All that to say that space is colorful. That's the theme of tonight. But a lot of these images that you'll see of nebulae and mostly nebulae, honest, are actually false color images, and those colors are added later for a reason, right? So that's false color imaging. That's why it's done. And other reasons it can be done is if the thing that's being imaged isn't even in the visible spectrum. And I talked about that when I did the James Webb episode, where James Webb doesn't image in the visible spectrum, right? A true color James Webb image is blank, right? We can't see it. So what they do is they basically take the various different infrared wavelengths and they transpose the visible spectrum onto that, right? So the bigger wavelengths of infrared, the far infrared gets redder tinting than the near infrared, which they tint more blue, and you get a color image, even though in reality it's all in a part of the spectrum that we can't see. So that's another reason to do false color imaging. And there are sort of standards and traditional ways of doing this in astronomy. So if your image has visible light and infrared, there's a tendency to color the infrared as red, right? Or orange or what have you. If you're taking radio waves, right, radio astronomy, and you're making radio wave images, there's a tendency to use red or orange. Which is actually why both of the black hole images that came out look like pumpkin spice donuts. It's not because they're, oh wow, isn't that interesting, black holes are orange. It's because the imaging they're getting is from a radio telescope. It's not in visible light at all. It's a grayscale image produced by combining the data of all the telescopes, and then they dye it orange, right? That's just by convention. I'm going to check the chat real fast and see if we've had any other questions. Cooper says, hi, what's up, Cooper? Good to have you tonight. Cooper, probably my most loyal fan. One of my most loyal fans, I should say. Always tuning in and watching the show. My dad, also a loyal fan. I'm surprised he hasn't made an appearance in the chat yet. But welcome. Good to have you tonight as well. Okay, so let's see. We talked about false color imaging. Let me consult my list of topics again. And again, feel free to just jump on this at any time and bring up some of these really interesting topics. Nebula color and composition, I'll touch on this real fast because I briefly mentioned it. So why is that nebula pink, right? Well, we now know why. It's because of what the nebula is made out of. Nebulae come in a few different kinds. That one that I showed you is something called an H2 region. H2, as we've learned a second ago, means doubly ionized hydrogen, right? So it's hydrogen gas. There are other things in that cloud of gas, hence why the false color image gave us more variety. Because some of the other things in there, like sulfur, also show up red. But nonetheless, it's an H2 region. It's got a lot of this hydrogen in it, and that tends to glow in the pinker, redder part of the spectrum. So to circle back to the topic of color in galaxies, we now have another thing we can look for, right? If I bring up one of my favorites here, Messier 83. In fact, Messier 83 is the channel logo. The logo of this channel is a painting I made of Messier 83, based on this image, actually, specifically. So this image is what I used as a reference when I painted the logo for the channel. Messier 83, you'll see that there's a lot of blue in there. There's a lot of these sort of dark streaks, and that's actually just gas clouds obscuring light. We call that dust. Interstellar gas and dust blocking light. You'll see a lot of the amberish color near the middle and all that blue. And if you guys remember what I said, the blue tells me that this galaxy is undergoing new star formation. It makes new stars, right? It's replacing its population of the big hot blue stars that don't last very long, right? But there's another thing to look at in this image, and that is, you might have noticed, all the pink. There's so much pink in this picture. Well, all these little pink blobs that you're seeing, those are nebulae. Those are like that Eagle Nebula that I showed you. But now we're looking at a whole galaxy, and so we're seeing all these little pink nebulae all throughout it. All these little Eagle Nebulas, basically, scattered throughout this galaxy, through its spiral arms. And H2 regions are where stars are formed. That gas collapses into balls, and those balls will gather more gas onto themselves until they get big enough to have enough pressure to heat up to the point of igniting and becoming stars. And so here where we see, and those stars will make the gas that they formed out of ionize and turn pink. So where we're seeing all this pink, that is specifically where the star formation is happening. So we know that new stars are being made in this galaxy because it has blue stars and they haven't all died off yet, right? This must be replenishing its population, like I said. But we can also see where that's happening. And what's interesting is we can see that that's concentrated to the spiral arms, right? But that can be useful when we see more complicated galaxies as well. Let me show you an example. Antennae galaxies. The antennae galaxies are really cool. Interestingly, or I find it interesting that a lot of pictures of the antennae galaxies don't show the antennae, right, that they're named after. This picture shows these two streams of stars coming off, that those are the actual antennae that they're known for. But if we look in the middle here at this image, what this is the antennae galaxies are two galaxies that didn't start off looking all weird with antennae. They started off fairly normal, big spirally guys probably, and they hit each other. They pass through each other. But galaxies are like clouds. They're like clouds of smoke. They don't have a physical solid form. They're made up of stars. And so, they will sort of pass through each other, warp, distort. Their gravitational pull will bend and distort each other, not even just from hitting, but they will literally just tug on each other and make all these weird, crazy shapes before they eventually settle down and form a bigger galaxy made out of the constituent material of the two. But if we look at this galaxy, I want you to look at where is the pink, right? Here we see, first of all, these two big yellow things here and here, those are the cores of the two galaxies, right? The cores have not yet merged into one. We see a lot of blue over here. We don't see as much blue over here. And that makes me wonder if one of these two galaxies was sort of done forming stars, right? It was not making new stars, not replenishing its blue population. But when they merge, there may still be good gas in this galaxy. There's an interesting thing with the gas in a galaxy that if your gas is evenly spread out, it will never form stars, right? It has to have something that acts on it, that compresses it, that causes a density variation that can then be acted on and grow to form these knots that will become stars. Well, a good way to do that is to slam into something else, right? Went the wrong way with that. So what I suspect happened with the antennae galaxies, based on color, based on what I'm learning by looking at the color, this is a true color image, is that probably one of these was a younger galaxy with plenty of new star formation going on, making a lot of blue stars, and the other might have been an old dinosaur galaxy. But when they hit each other, that impact and the gravity, not a physical impact, but when all the gas in one galaxy and the other galaxy, when those gas clouds came together and the gravity acted on them, that gave the impetus to ignite a bunch of star formation. And we're seeing that here and through here in the form of this pink color, right? So now, this is why I wanted to do this episode. So um, now you guys hopefully should, when you look at images of galaxies, you're not just going, ooh, pretty. You now have the knowledge to kind of learn something about that galaxy just based on the color. Checking the chat, we've got some conversation. Cindy's here. Hey, Cindy. Finally got finally got on the chat. Is the core like a sun? Probably a stupid question. Well, I forgot to say this at the start of the show. I do not believe in stupid questions. The only thing I would consider a stupid question is a dishonest question, like a gotcha or something like that, where you're just trying to be difficult. A person who genuinely wants to learn is never asking a dumb question. They are asking a question from a position of wanting to learn. That's what questions are for. So the core is not a sun. Galaxies are actually really, really big objects, which you're actually seeing here in the core. I'll bring my picture back up for me. You guys are still seeing it. This glow is made out of hundreds of thousands of stars, right? Or maybe, yeah, hundreds of thousands of stars. A lot, right? Maybe even millions. I'm not sure what the right number is. Probably more in the millions, tens of millions, something like that. All together, such that you cannot make out any individual stars. And the light of so many stars packed together produces this bright glow. But if we zoom in a little bit on this picture, every single dot is actually a sun, is a star. Remember that the sun is a star, and so every single little dot in this picture is a star, right? And so the core, we can't even make out the individual dots anymore. They're that densely packed together in the core. And their light, the glare from all those stars, is preventing us from picking out individuals in the core. So that's an excellent question. Let me go back to the chat again and see what else we have going on here. In the collision area, I see much pink, which is probably caused by all the gas from both of them. Okay, cool. So Cooper, I wasn't watching the chat when I was explaining that, but it looks like Cooper came to the same conclusion. Excellent job. You are absolutely right. That's from the gas from them getting compressed into a small area, just like you said. Yeah, and then Cindy says, "Oh, it's that massive." Yeah. Oh, space is so big. It's it almost seems like one of those like things that's true, but it's trivially true. But space is absolutely mind-blowingly vast. It's difficult to understand how big space is. And I can show you some charts in which the galaxies are dots. And literally, you cannot make out any individual stars. The vastness of the cosmos is absolutely jaw-dropping. But but nonetheless, this is a way we can look at images of galaxies and get some ideas about them based on color, right? And to that end, you know what we might do that might be fun? Let me see if I can bring up some more galaxy images and see if we can make some guesses about them based on their color. Stephan's Quintet. This is one of the things that that the James Webb imaged. And actually, of course, the James Webb pictures are all over here. Now, the James Webb is imaging not in the visible spectrum, but is applying false color. But for this exercise, I want to look at it in true color. So let's take a look in true color. So here we go. This is our image of Stephan's Quintet. And right out of the gate, we can see some things going on here with color. We can see that this big guy right here, this big spirally guy, is blue, right? And we see all the little pink in there. So this is very much like M83 that we looked at before. This galaxy is no doubt a very young galaxy. Or if not young, it just has a good supply of, well, young. Okay, so let me explain. How do we know that a galaxy that's still making stars is young? Well, because galaxies use up the available gas within them to make stars, right? So that's how we would know that that's young, right? So this galaxy is young because it's still able to replenish its supply of blue stars. This galaxy over here is not. And usually we tend to see that the spirals are blue and the ellipticals are amber, right? Like this guy down here kind of fits our expectation, but this guy's got spiral arms on him. So what's going on here? Well, usually if we see something like that and it's not blue, a lot of times it turns out that it's because it's interacting with something else. Now, we have clues other than color to tell us that. We can see the big stream of material coming off of here. When I say material, literally suns, stars, thrown out into the void. Imagine that. We can also see this disturbance going on over here. And this I find very interesting. I'm going to zoom in a little bit. Are we going to zoom? It's running a little slowly because these images are very high res, which is good. It was good for our purposes today. I don't think it wants to zoom in for me. So we see little knots of blue and pink here and here, but not so much in here. And what that suggests to me is that maybe neither of these two galaxies is a particularly active galaxy for star formation, but that the interaction with another galaxy is triggering more star formation. And this is very typical. If we look up any pictures of interacting galaxies, oftentimes you will see that the interaction correlates with star formation, with a lot of blues and a lot of pinks especially. Let's check out the Cartwheel Galaxy. Right, here we go. Right. So what happened here is one galaxy just went clean through the other. And the mass of the galaxy as it came through concentrated material towards the core. That's why we get like an outer ring and this like more dense inner core, because this guy went shooting right through there. It also got messed up, but man, look at the pink going on in here. Now the whole thing has gone a little bit red, and I can talk a little bit about why that is. And actually this, I think, oh, it's a James Webb image. Oh goodness, okay. I might be off base here with what I was going to say. Look at all that pink from star formation, but actually Hubble makes it look bluer. So I'm not gonna, I try to always be intellectually honest on this show. I'm not gonna speculate if I don't know. So I don't actually know what's going on here star formation wise, but now I'm curious. Now I want to know. But nonetheless, you get the idea. When we see a lot of galaxies interacting, merging, let's just try merging galaxies. We often get a lot of pink colors associated with those mergers. Because it can trigger new star formation. Let's see here. Going back to the chat. Looks like a car tire. Yeah, or a cartwheel. That's why they call it the Cartwheel Galaxy. So like a cartwheel, a bike tire, a car tire, right? It looks like it has a rim and spokes. All right. I'm going to go back to my big list of topics and let's see what else. We've got about an hour left in the show, and we're kind of just smashing through some of these topics. So don't be afraid at all to ask follow-up questions or ask me to elaborate or ask questions that maybe don't have to do with color, right? We've got a lot to talk about, but I'm not married to getting every one of these done, right? I want to make sure that you guys have a chance to be part of the conversation. And to make sure that I'm not just talking and you guys aren't just retaining anything, right? Like, do ask questions. I want to be, feel free to interact. Let's see here. We talked about galaxy color. Let's talk a little bit about spectroscopy, and we'll also get into redshift. I touched a little on spectroscopy, but I'm going to go back and talk a little bit more about it. So another piece of information that we can get from color is we can look at the colors in a star to figure out what it's made out of, right? So let's take sun spectrum. And some of you guys, I bet you didn't realize there was this much to talk about just on the topic of color in astronomy, but that's why I wanted to do a whole show. The more I thought about it, the more I thought, man, there's a lot to do with color, right? It's actually a lot of astronomy pertains to color. So here's our spectrum of the sun, right? The sun's spectrum is at the bottom, and we see these lines. And I mentioned earlier that every chemical element has a characteristic set of thin black lines that show up if it is absorbing light. Now you might think, wait a second, the sun isn't absorbing light, the sun's emitting light. Why do these look like absorption spectra? Why are the gases that are in this, why are these chemical elements in the sun, technically not gas, they're in a plasma state, why are they absorbing light rather than emitting it? Well, the truth is they are emitting light, but the brightest part of the sun is not its surface. The brightest part of the sun is the core, right? What happens is the core is the part that's undergoing nuclear fusion. Now that heats up the rest of the sun and excites it to a plasma state. That's cool. And that's going to contribute to the overall color of the star in terms of the broad spectrum. Does it look a bit more red or blue? But shining through those outer layers is light that begins in the core of the star and then gets emitted, absorbed, re-emitted, reabsorbed, re-emitted, reabsorbed, and works its way out through the star. So, when the sun's light shines, the materials that compose the outer layers and the inner layers are going to absorb some of the colors of that light that came from the core and is now shining, right? So what we get is that the overall spectrum of the sun, now the sun is actually just going to be super bright across the board, really, but the spectrum is going to be dimmer and is going to be essentially missing bits of the full rainbow, right? Bits that were absorbed by the chemical elements present in the sun. So what we can do is we can take that white light from the sun and break it up into the whole spectrum. And I actually have a device that does this. I have it's a cheapo. It's not really a scientific grade for making like really accurate measurements. It's for demonstrations. And I like to bring it with me to Hannah Park. And while we wait for the sun to set, I can have people look through it, never look at the sun with it, but we look elsewhere because all the light is ultimately coming from the sun. And people can see for themselves that, yeah, the light is actually missing colors. There's these little lines in it. Well, every chemical element has a different pattern of absorption lines, right? This is the pattern for hydrogen. This is the pattern for helium. This pattern is associated with sodium, etc., 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 right? So, what we can do is we can look at the lines in the sun and we can find these fingerprints. And this is how we know what stars are made out of. What's even better is if we use a very sensitive instrument, we can find out the degree to which that particular wavelength has been attenuated, right? Has it just been squashed completely or just a tiny dip in brightness, right? What are we dealing with here? And we can actually figure out the amounts to which these elements are present in a star. So if I actually bring up a picture like this, rather than just showing it on a rainbow with little black lines, we can actually see, again, this one apparently not in English, but we can see these dips, right? These areas where there's like a clearly, you know, this is the whole spectrum curve, right? This is how much the sun would just normally emit throughout the thing. And then we get these little gaps, these little dips, right? And then the depth of that dip tells, and this is actually not the sun, I don't think. Is it? I don't know. Because there's a lot here about water, but we can tell based on those dips. Let me see if I can find one in English. Or we could invert the chart like this, right? And see the relative amounts of the different chemical elements. And that will tell us exactly what the composition of a star is, right? All these things we know about stars, that they're made of hydrogen, that they turn hydrogen into other stuff, and all these things, comes from analyzing the spectra. If we find stars that look like they're more evolved, a little bit later in their life, their composition is going to be different from a younger star, right? This is how we know our sun's about halfway through its life, because how can we tell, right? Throughout the whole life of the sun, it doesn't change colors until the end when it swells up, turns red, and kills us. But how do we know that the sun's about halfway through? Well, we can analyze how much hydrogen and helium are in the sun. The sun's going to convert hydrogen to helium. We know that most of the sun is actually not going to undergo fusion at all. That only happens in the core. But given the volume of the core, looking at just that, we can figure out what the proportions ought to be. And we figure out that the core is about halfway done. It's about halfway through its hydrogen supply. I've mentioned helium multiple times now, and I am talking about spectroscopy. So, you're coming to the camping thing. Excellent. Yes, I did get your mom's email, Cooper, about that. So that's really good. She's on the list. Need to get the information from you guys, but we'll talk about that outside the show. All right, so, but I mentioned helium, and I'm talking about spectroscopy, so I have to tell the story of helium. So, when scientists first analyzed the spectrum of the sun, they were able to identify certain elements. But they found that there was one element that they didn't know what the heck it was. Right? There was a pattern of lines, and again, if we take our chart, right, it's this pattern. It's these lines right here. Didn't match any known element. And so they said, well, we've clearly found a new element, right? And so that element is named helium because Helios means sun, right? Helios was the Greek god of the sun. The solar system model that puts the sun in the middle is called the heliocentric model, sun in the center. So helium. Elements tend to have eum at the end of their name, right? Well, then they found it on Earth. And the reason why they know it was the same stuff is because you can actually tell, based on the pattern, what chemical properties this should have, right? How many protons and therefore how many electrons. And so they knew from analyzing these lines, like, we found a new element, 2 protons. We've only found it in the sun, so name it helium. And then, son of a gun, we end up finding it on Earth, right? We find helium deposits on Earth. And so now you guys know a really fun fact you can tell your friends, that helium was actually found in the light of the sun before it was found on Earth. And that's why it's called helium. Fun fact. And I said I was going to talk about redshift, didn't I? I wanted to talk about spectroscopy, so let's talk about redshift, because spectroscopy naturally leads into redshift. So what often happens, and this picture, by the way, gives a really good idea. This is the real truth. When you break up the spectrum of the sun, you have to, like, do multiple rows like this to get the full, right? These are, like, more simplified pictures, and all these, like, dark lines. There's actually more going on there, right? So this is more like what scientists are looking at. And even this is just a visual representation. Really, they're looking at charts like this. Okay, so, and this picture talks about it. Excellent. Okay, so some scientists, and by some scientists I mean Edwin Hubble, noticed that if you take the spectra of stars, that for many of them, all the characteristic lines are there. That is clearly hydrogen. That is clearly helium. That is clearly iron. But the individual, it's the same overall pattern, right? The 2 by each other, then 1, whatever. That pattern is correct. But it's not where it should be. It's slid over to the red end of the spectrum. Or sometimes that pattern is there, but it's slid over to the blue end of the spectrum. And that's what this picture is showing, right? Here we see, this is what we should see. We get this exact same pattern, but it's too far into the red, right? It's slid from where it's supposed to be. It has red shifted. It is shifted towards the red. What's happening here? Well, we can use an analogy to really understand this, because remember I mentioned that light travels as a wave. Light's also a particle. That particle is called a photon, but again, not getting into quantum physics tonight. Don't drag me into it. So, because light is a wave, another wave that we're all familiar with is sound, right? Now, sound is a pressure wave. It propagates as a pressure wave. Light is a quantum mechanical thing, and it's weird, but the analogy still stands. So, if you've ever been outside, rarely, right? No, if you've surely been outside before, by the street or whatever, or maybe in your home or somewhere, you've heard an ambulance or a police car drive by. Right? This is an experience you've no doubt had. And what do we all know about that siren, right? When it's coming at us, it's high-pitched, and once it goes, the pitch drops, right? You get that as it goes by. Well, the reason why it does that is because as the, I'm going to get a visual for this too. The name is the Doppler effect, spoiler alert. So let me get a picture of the Doppler effect. Why are we looking at swans and stuff, man? Okay. Doppler effect. The usual visual for this is a siren. You usually see like an ambulance, right? Okay, nobody has an example of the Doppler effect with an ambulance. Okay. I'm honestly really surprised. Maybe it's because of my spelling. I'm not really sure. Here we go. This does an okay job. All right. So here we see the I can't make this any bigger. Okay. We see the car is emitting sound waves in all directions, but you see as it moves forward, right? You see how the sound waves, you see how far apart they are normally. As it moves forward, you see that they bunch up in front of it. The reason why is because it emits a wave, but it follows that wave, and so they bunch up in front. And then you see that the waves stretch out behind because it emits a wave and then runs away from it before emitting the next wave, right? This is what causes the Doppler effect. The sound waves bunch up in front of the ambulance because it's going after them, and they stretch out behind it. And so you get a high pitch when it's coming towards you, and you get a low pitch when it's going away. Well, if an object in space is moving towards us or away from us very fast, then the light waves themselves will bunch up or stretch out just like the sound waves from the ambulance. And if you recall, we talked earlier about the spectrum, that the short wavelengths of light, I'm just going to bring up spectrum again. Spectrum. The short wavelengths of light are bluer, and the long wavelengths are redder. So, knowing what we know about the Doppler effect, that tells us, with light being a particle, wouldn't it accumulate on a lens over time and have to be cleaned off? That is a very interesting question. I appreciate that question. So, luckily, no. First of all, the particle of light passes through a lens. A lens is transparent to light. So that photon will actually pass through. This actually has to do with the fact that objects are not actually solid, right? When we think of a solid object, that object is made up of atoms, but atoms are almost entirely empty space. You have the core, nucleus, with electrons whirling around in a cloud, and then those electrons will go back and forth to other atoms, and that's what kind of joins them together to form molecules and a crystalline structure like you get in glass. And the photons just go right through it. What the glass of a lens will do, though, is it will bend that light, and that's what causes it to focus. In fact, the photon will eventually go and hit your retina, and then there is a pigment on each of your cone cells. It's actually a pigment that does this, that absorbs the light, and the molecule changes shape when it does because of the energy imparted by that photon getting absorbed. So that's actually what happens to the particle. If you want to think of photons as a particle, they actually travel hundreds of millions of light years, come in through the atmosphere, pass through all the air, go into your telescope, go bouncing off the mirrors, through the lenses, and they die on your retina. But the energy of it isn't lost. The energy is then transferred to whatever that photon hits, right? So that's actually what happens to the photons. So very interesting question. But no, you don't have to clean photons off of your lens, thankfully. The glass is transparent to light, and the photons just pass clean through. So what I was saying about the redshift, so given what we know about the Doppler effect, we know that the ambulance sounds deep when it's moving away, so the light should look red when it's moving away. And what's really interesting about this is that Edwin Hubble figured out that all the galaxies around us, for the most part, the average, the more common scenario is that they're redshifted. Some are actually blue shifted because they're heading towards us, like an Andromeda galaxy. But overall, the universe is, for the most part, redshifted. The general trend is redshift, which is that everything's running away from us, right? And what's even more interesting, and I could really dive down this rabbit hole, but Hubble figured out a way to tell how far away these galaxies are. He used variable stars. They're called Cepheid variables, and basically they have this really interesting property where they pulse, and the rate that they pulse is directly tied to how bright they are. So you can time them, figure out how bright they are versus how bright they look, and you can figure out how far away they actually must be for the light to be that much dimmer by the time it gets to us. And so he was able to use these to figure out the distances to different galaxies. And he found that the further away a galaxy was, the more red-shifted the stars, when you analyze their spectra, were. And so not only is everything moving away from us, but the further it is, the more it looks like it's moving away from us. Well, it's not that we're the center of the universe and everything's running away from us, right? What's really happening is everything is running away from everything else, right? And so if everything is running away from everything at the same rate, everything's moving away from their neighbors at the same rate, then the further things would appear to move further, because if, like, you imagine, like, I'm standing next to somebody and somebody's standing next to them, and I'm like, hey, can you move over? And he says the same thing. He will move, say, 4 feet from me. But the person that was next to him, if they move 4 feet away from him, they're also moving 8 feet away from me, right? So the further down the galaxies are, the faster they appear to be running away from us. But the reality is that everything's running away from everything. And that's how Edwin Hubble figured out that the universe is actually expanding, right? The expanding universe is something we now know about because of this redshift. Redshift tells us a lot of other interesting things as well. We can tell which direction a star is rotating, because the light coming from one side of it will be slightly redshifted and the other side will be very slightly blue shifted, because one side's moving away and one side's coming towards us. Same thing with the spiraling of galaxies and these kinds of things. This is how we know that the Andromeda Galaxy is coming at us, because it's blue shifted. It's coming towards us. The other interesting thing, though, is that you can get these long lines because something is moving away. But the other thing that can happen is that this wave is traveling through space, and then space itself stretches and will stretch the wave en route, right? That it was one wavelength when it was originally emitted, and then as it traveled to us and the universe expanded, the expanded universe stretched it and turned it red. And so that's the other reason why these distant galaxies are redshifted. It's not just because they're moving away. It's actually because space itself is expanding between all the galaxies, causing this redshift effect, right? Which I think is a really cool topic. And another, no problem, dude. Like I said, I love to have the chat active. I love it when you guys are participating, when it feels like a conversation. I'm not just out here talking to myself for 2 hours. That's the best, man. So definitely keep the questions coming. And that was a very interesting question, and that got us talking a little bit about how lenses work. So I really appreciate that. All right. So that is talking a little bit about redshift, which, again, another fascinating color topic in astronomy. What else do we have? Talked about that. We talked about nebula color. Why is Mars red? Why is the sky blue? I put it on the list. It's not actually... these last questions aren't super astronomy necessarily, but they are still interesting questions relating to color, and they occurred to me, so I put them on the list. Again, feel free to drop in a question if you got any other questions, but why is the sky blue is a good question, right? So let's talk about that one. The sky is blue due to something called Rayleigh scattering. So basically what happens is the photons of light, as they reach us from the sun, we don't often think of the air as a solid thing, right? The air is just sort of, we don't think about it, right? An analogy that I heard one time that I thought was just absolutely brilliant is this guy was giving a demonstration. He said, what is the one thing fish don't know, right? What is the one thing fish don't know? Fish don't know that they're wet, right? They have no idea, right? Because they live their entire lives in water. To a fish, water is nothing, right? Water is just what's everywhere. They don't think about it. And we never think about the fact that we are soaking wet with air, right? We are constantly around. If we go into a vacuum, we will notice. Just like if a fish gets out of water, he will suddenly realize that he is dry. But generally speaking, we don't notice the air because we're just accustomed to it. It's there and we can see clean through it, so we don't tend to think of it. But the air is a substance, right? So when light passes through air, it is not unaffected. What happens is these light rays, and again, because of quantum physics, you can either think of them as waves coming in, or you can think of them as discrete particles. Both analogies work, and are both true in a wacky quantum kind of way. But the photons of light, or the particles of the waves of light, will interact with the molecules of oxygen and nitrogen and carbon dioxide and these things in the Earth's atmosphere. Earth's atmosphere is mostly nitrogen, and the second most abundant, I think, is it's nitrogen, oxygen, with some trace carbon dioxide and other things, although more CO2 lately than is typical, and that's causing a problem. But generally, the atmosphere is mostly nitrogen and oxygen and some other stuff. CO2 is, I think, third place in terms of most common. So as the and water, H2O, water vapor. So as the light's coming in, it's going to get absorbed by the oxygen molecules in the air and then emitted again, right? So it's absorbed and emitted, right? Because the oxygen gets excited, the electrons jump to a higher energy state because they absorb the light, and then they fall right back down and re-emit the light again. And what happens is oxygen and nitrogen have a tendency to absorb the bluer wavelengths and scatter them again, and to not be as affected by the yellow and the red part of the spectrum. So what happens is the sun's light is white, right? If you were to get out to space and somehow observe the sun without, burning out your eyes, but if you were to see the sun from space, and astronauts have reported, like through tinted, glass and things, they've said the sun looks white in space. It doesn't actually look yellow unless you have a yellow tint, right? But what happens with the atmosphere is that the blue light gets scattered by the oxygen and the nitrogen. So that blue light, it does eventually make it to the ground, but it makes it by scattering and scattering and scattering and bouncing and moving around. So the blue comes at us from everywhere. So everywhere we look, we see the blue. The yellow takes the straight road and comes straight down from the sun. So that's why if you glimpse the sun, and you should never, ever stare at the sun, but at some point in your life, you probably lit up and gone, dang, and you saw it, right? You're not going to go your entire life without seeing it. Probably thought it looked a bit more yellowish, right? And children draw it with yellow crayon. That's because that light isn't being scattered like the blue part of the spectrum is. So that's the actual reason to why is the sky blue. One of those classic questions that, is a children's question, the thing that we ask when we're kids that now you know the answer to. Cooper says, why are there no purple or green stars? I actually did cover it earlier, but I'm always happy to repeat and go back. So the reason why, I'll actually get more into it, actually. That's a really good question, so I want to really do it justice. And it may end up being the last thing we talk about tonight. We'll see. Because I want to do my usual outro as well. For those of you guys who are still with us, definitely appreciate you guys sticking out there. Feel free to say hi in the chat again. Let me know you're still here or whatever. Or ask a question. You don't have to be quiet. Like I said, I would love it if I hopped on and the chat's just rowdy. You guys are talking and participating, and I want it to be a hangout. All right, we're going to look at something called a black body curve. What is a black body curve? So, what this is what light would look like emitted by something called a black body. A black body is a theoretical object. It's impossible to make a true black body, but essentially what it is it's something that would emit no light at all, and would be utterly black unless you shine light. It's kind of like, imagine a box that would trap a photon and it would eventually come out. But the basic version is that an object that emits light as a full spectrum rather than just parts of the wavelength is going to emulate a black body scenario. So stars approximate a black body. They're not true black bodies, but they approximate a black body. And so a star is going to emit its light. This picture really shows what I'm trying to talk about. It's going to emit its light throughout the spectrum, right? So can you guys see this all right? It's not getting cut off? Okay. Because I do have it cropped a little bit on here so you're not seeing like the address bar and stuff. So these are black body curves. And a true black body should only emit based on its temperature, right? That should be the only determining factor in the wavelengths of light that it emits. Now what happens is you'll see that for each of these black body curves, they put out the entire visible spectrum, right? The visible spectrum is not missing from any of these. There's no color missing from blue. This blue line, right? This green line is not missing any colors. This reddish line is not missing any colors, right? There are no colors missing from any of these black body curves. But if we take this green line as our example, we see that it's putting out the red part of the spectrum far more than it's putting out the blue end. Now, what's going to happen is because it's putting out every single color of light, they're all going to blend, right? All those wavelengths are going to sort of blend together to white. But the over concentration towards the red end of the spectrum is going to make the red part stand out versus the blue, right? Once it's all blended, you get more red left over, right? Another way to think about it is if you imagine that like things towards the red end and things towards the blue end will cancel each other back to white. If you want to think of it like that, like in math, like positive and negative numbers cancel out. When the canceling's all done, you're left with red left over after that's all done, so that star appears red. This bluish line right here, the peak is in the middle, which means that when everything cancels out to white, you basically end up with yellow, right? But the flatter the black body curve, the more it's going to just be white, right? And then you can imagine the opposite of the green line here, which would be this line that goes off of our chart, where, again, after all the cancellation is done, we're mostly left with blue. But what you're not going to get with a black body curve, what you're not going to get with a full spectrum emitter like a star, is a case where you're lacking in red and blue, but you do have a very strong through line of green, right? If a star's peak is in green, it's going to have wings in the red and blue, and it's going to come out as white, right? So that's basically why we don't get green stars. The reason why we don't get purple stars is because purple basically doesn't exist. That may be that might be the most shocking thing I've said all night. What is going on with Beetlejuice? Yeah, we could talk about Beetlejuice too. Cindy's here also. Excellent. Cool. Barbara, glad to have you. Jamie's here. Awesome. Very cool. All right. Yeah. See, I like to see who's here, man. According to YouTube, I've got 9 people watching right now, so I'm definitely not alone. All right. So I'm going to wrap this up. I'm going to talk about Beetlejuice real fast. So, basically, we don't get green stars because stars are broad spectrum emitters. They're going to give us basically white, red, or blue. That's it. And then I made the very controversial statement, possibly controversial statement, that blue is fictional, right? The blue, or not blue, purple. Please don't quote me and say blue is fictional. Purple doesn't exist. And what I mean by that is, like, unlike the rest of the colors of the visible spectrum, purple is a made-up color, right? Purple is a color that our brains have concocted to explain what happens if our red cones and our blue cones are activated, but the green cone is not. Right? What do we do if our spectrum is a saddle? Right? We get a lot of blue and a lot of red, but not the middle. And our brains have sort of made up this purple color for that scenario. Right? But if you have the middle of the spectrum, you will never get purple. Right? Purple requires the exclusion of yellows, reds, and greens from the palette of colors sort of coming through. So that's why we don't get purple stars, right? And why we don't get green stars. Now, Lizard Rock from the Lizard is asking for, I love that screen name, by the way. I hope you have a channel about like herpetology or something. I think that'd be really cool. I'm going to check you out after we're done here. But Lizard asks about Beetlejuice, right? What's going on with Beetlejuice? So what's going on with Beetlejuice currently is not much, right? I did mention earlier in the stream how when the star turns red, that indicates that it's dying. And that is what's happening with Beetlejuice, right? Beetlejuice is a red giant star, so Beetlejuice used up its supply of hydrogen in the core and began turning the helium that it made throughout its life into heavier elements. And the outer layers have swelled up and turned red because they cool as they swell, and so we have a red giant situation, which, as we said earlier, is the indication that that star is dying. That star is near the end of its life. The problem is that the red giant phase can last varying amounts of time depending on the mass and composition of the star. Smaller stars can't go as far up the periodic tables, smashing together heavier and heavier elements, as the big stars can. So, but they also go through their fuel at different rates because they don't burn as hot. So I actually don't know what the time frames are with the different time frames. That's something I should research more so I can better answer this question in the future. But basically, a star could be in that red giant phase for thousands of years, maybe even millions of years before they eventually, well, I don't think millions, but they can be in that state for a really long time before they eventually pop. Um, so with Betelgeuse, it could detonate tonight, or it could not detonate for 2,000 years. We just don't know. And Betelgeuse varies in its overall size and brightness because of this process that goes on in the core where core collapses, heats up, does more fusion, collapses, heats up, does more fusion, and it kind of makes the outer layers pulsate, which makes it difficult to gauge the true size of Betelgeuse and difficult to gauge its true distance. Betelgeuse is actually a notoriously difficult star to pin down. So there are estimates of its distance that kind of vary between like on the short end, you'd see things like 300 light years. On the long end, you see things like 600 light years. And that's going to throw off mass estimates as well. How big is it really? And again, I'll admit a little bit of ignorance. I don't want to get too into that kind of things. I don't want to say a bunch of stuff that's not really correct. But unfortunately, it makes it very hard to predict like how much time does Betelgeuse have. But the answer to the question with Betelgeuse is basically that. Now, a few years ago, and I say a few years ago, it might be longer than that, man. I lose track of time. But there was a time when Betelgeuse started dimming a lot. And it dimmed like not like if you analyze the light, okay, we can tell it's a little bit, in the readout of the instruments. It was like you could look up and be like, man, Betelgeuse doesn't look okay. It just kept getting dimmer and dimmer and dimmer and dimmer. And a lot of people were like holding their breath and crossing their fingers like, is this it? Is Betelgeuse going to pop? Because if Betelgeuse pops, let me tell you, it's going to outshine the full moon. It's going to be a show, right? And then it'll fade and you won't see it anymore. It'll just be gone from the sky, right? But then Betelgeuse came back. And it turns out that dimming was just a temporary phenomenon. I forget what the exact explanation ended up being, because a lot of professional astronomers were really studying this. Right, it was the one person who first noticed the dimming, like joked that she would go outside and keep checking on Betelgeuse to make sure it was still there, but it did bounce back, and it's thought that it could be, and I think they might have actually settled it, but I remember that the hypotheses were. It could be a very large star spots. You know how the sun has sunspots? If you get a big enough sunspot group, the overall brightness will appear dimmer because you've just got a lot of that light blocked by the sunspots. And so there's this thought that maybe Jupiter, for whatever reason, just produced a very dense region of star spots on the side facing us, and that those then evaporated as they naturally do. Another hypothesis is that there might have been some sort of gas or something between us and Jupiter. It can be easy to forget that these things in space really are moving, even though the stars look like they're just fixed because their orbits are over the course of millions of years. They do move, and so too do things like the interstellar medium, these gas clouds and things. So it's possible that maybe some gas passed between us and Jupiter, and Betelgeuse, temporarily dimming it. Another hypothesis is a comet, that Betelgeuse might have had a large comet, because Betelgeuse is a star, so there would be things orbiting it, like cometary material and things left over from its initial formation, that a comet orbiting Betelgeuse might have outgassed and put a big cloud of vapor between us and Betelgeuse, temporarily dimming it. I can't remember if that one ended up being what they're now saying is probably the case. I will admit ignorance in this and say I don't know. So hopefully that does a decent job of answering that this might do a decent job of answering that question of what's going on with Betelgeuse. Rip anyone that's looking at Betelgeuse during the explosion to a telescope. Well, again, it would outshine the moon, but it wouldn't be like the sun. It wouldn't damage your eyes, but it would be bright. Help desk says, couldn't it be plausible that the star like Betelgeuse isn't powered by this explosion, but rather they dim and brighten and explode due to the unseen electrical current hitting it? Uh, I'm gonna guess that this is a reference to Electric Universe. Um, I don't have time left in the stream tonight because it's gonna end at 9:30 to give Electric Universe the thorough debunking it deserves. But the short version is Electric Universe is a fringe theory, and it is not accepted astronomical science. And essentially, it's false. It's not the case. Um, Maybe an electrical current could hit Betelgeuse from somewhere, I guess. But the Electric Universe basically posits that stars are not powered by fusion, but that they're electromagnetic phenomena, and we just know that's not true. We know what stars are made out of. We know how they function. We know the stellar life cycle of a star. They are not electromagnetic phenomena. They are fusion based. So we know that the source of light in stars is a nuclear fusion reaction. Um, Now, it is true that the star itself is a plasma rather than it being just a pure gas, that it's excited to a plasma state because it's hot enough. And stars do generate an electromagnetic field around them. They have magnetic field lines. This is actually what causes things like sunspots. But the primary powering mechanism within a star is a nuclear fusion reaction. Um, and it's not an explosion per se, because the star's own mass prevents that. There's an equilibrium state between the energy produced by the fusion reaction and the mass of the star crushing in on it, basically. No, I know you don't. I hope I didn't come across like I was suggesting. I'm sorry, but I always assume in our chat good faith when it comes to the questions, um, regardless of what the question is. And if somebody were to come into the chat and ask something about like how do we know that the Earth is round, I always want to take that as an educator. I take that honestly and try to answer it. So that was also for your case as well. Just so you know, if you've been seeing a lot of this Electric Universe stuff, I do highly recommend looking into some of the videos that debunk it, because it is sort of a this sort of fringe thing. But no, I don't think, I didn't suspect that you were coming in to troll or anything like that. I've seen a troll in the chat, thankfully not of one of my videos, but you didn't come across that way to me. It seemed to me like an honest question. Because like I said, we're all here to learn, and part of learning is not knowing things, right? Or having the courage to ask something that may be a little out there and learn. So yeah, but I just say that I would like to, and I might have to do an episode. I want to do a lot more research so I come prepared. But I might do an episode on Electric Universe one of these days. The only thing is, like I said, because you're clearly not trolling today. I have seen other channels get the troll rush when they start talking about flat Earth or Electric Universe and that kind of thing, and I don't know if I want to invite that. But it might be an interesting topic to cover. All right. Well, we've got about 13 or so minutes left in the stream. I can't math today. 12 minutes left in the stream. And with some of that, I am going to do a little bit of housekeeping and sort of start to wrap it up a bit. While I do that, if I see that somebody asks a question, I might interrupt myself to address it. But I want to remind everybody that I am on the board of directors of the Northeast Florida Astronomical Society. So if you live in the Jacksonville area, and apparently we've had guests tonight from outside of the state. We've had somebody who says they're from Arizona. If you're not in Jacksonville, drop in the chat. Where are you? And I'm always curious. Had one person tune in from the UK one time. So pretty cool stuff, man. But I want to remind everybody that we are the Northeast Florida Astronomical Society. You can check out our club on nephis.org. Once this loads, our logo will appear here, and you can read the website off the logo. But it is NEFAS for Northeast Florida Astronomical Society.org. And we do public education and outreach. Here it is, right there for you, nephis.org. We do public education and outreach. We set up telescopes for people. We also are a club of amateur astronomers. We're an astronomy club and also an educational organization. We're a nonprofit, and our membership, if you are interested in joining the club and being a part of what we do yearly memberships. You can go to Join NEFIS, fill out the form, join that way. And what you see there for membership dues, that is annual. Let me talk about our calendar, though, and talk a little bit about some of the upcoming events, just to remind people and anyone who may not have been here at the beginning of the stream. Again, if you do live in the Jacksonville area, because, for example, people are saying, wow, when and where the next meetup? Max and I are in Washington. Oh, Matt, is Max your friend? Is that someone that you know? That's awesome. Go to the outreach. We will show cool stuff. Yeah. Cooper is right about that. Cooper, that camping thing. So that's for membership. That's a thing right now we're doing as a start party for membership. It's like a trial run. We may do one in the future though with camping, but for right now, that's not actually something that's available outside of club members. That's all right though. But yes, we do have a start party coming up for our paid members. It's sort of a trial run with this park. They're having us camp out there and do like an outreach for their people, and that's to build a better relationship for them because we want to have more star parties there. But at any rate, some of the things coming up. Today is the 15th. Again, I do this the third Thursday of the month. So the next live stream is going to be, and it's always the third Thursday, so it's going to be the 20th of October. We do have a dark sky observing session coming up this weekend. I won't be going to that. I've got other things going on, but I will definitely try to make the one next Saturday. These are, of course, weather permitting, and you can click on them for more information. If you're a member of the club, I also send out emails for like go and no go and letting people know about them. But the big thing coming up, if you live in the Jacksonville area, the thing you're going to want to come out and check out is Hannah Park on the 1st of October. The 1st of October is Observe the Moon Night. And we are going to observe the moon. We're going to observe a lot more than the moon, but because it is Observe the Moon Night, I'm going to brush up on my moon knowledge for one thing. And we are obviously going to look at it. We're going to talk about it. We're going to learn a ton about it. And we're going to try and, we've been promoting the daylights out of this. So if there was ever a time to come to Hannah Park for just an astronomy blowout, man, come to this. And we have a rule about Hannah Park, and that is NEFIS never cancels. So we have been out, unless it's literally not safe. We canceled one time because there was like severe thunderstorms. But otherwise, if it, like hurricane conditions, we won't be out there. But otherwise, we are always there. To give a good example, we had one night we went out there, it clouded over completely and started to drizzle. We all went under one of the pavilions, put out a big lantern so that everyone could see us, and I did this show basically in person. I just started fielding questions and talking about space. No matter what, we will be hanging out talking about space. So don't be afraid to come on out. We have a good time no matter what. But obviously, if we can see the sky, we're going to look at all kinds of cool stuff. And then on the 7th, we're going to have our general meeting. That's our club meeting. That's also open to the public. The board of directors meeting is not. That is for the board members and club members only. Club members are allowed to attend our board meetings, though, and you can have your voice be heard and see how the sausage is made. And if you're thinking about running for the board, check it out, right? See how we do it and take part in the discussion. But the general meeting is on the 7th. Let me find out what we're talking about, because we always try to have a speaker. Speaker looks like it's to be TBA at the moment. So if any of our club members are watching this and you have a really cool idea for a topic, let us know, man. We always like to have good speakers. And then we've got s'mores and stargazing. This is something being held by the Little Talbot Island State Park. And I don't know if this is a public event or not. Maybe check the information about it. Still kind of bare bones now. We're going to figure it out. But we did this before where they basically have like an organization that raises money for that park. And they had a bunch of s'mores, and we set up telescopes for them, right? For their organization. And they loved it. So they're going to have us come out and do that again. At least I think they did. They said they did. And then again, dark sky observing and this. And Fort Clinch is going to be another big stargazing event that we're going to do. That one is public. You can go to Fort Clinch and take part of in that as well. But that's getting up to where my next live stream is, so I will talk about more on that day. But because it's right after the live stream, I guess I'll let you know about it now, and it should be a lot of fun. I try to make it to all of our outreaches when I can, unless we're double booked, and I do a laser pointer tour of the sky. So this is one of the things to check out at Hanna Park, for example. I have this outrageously powerful laser. You can see the beam right up into the sky, and I do like a laser light show, basically, and I draw out the constellations, talk about them, crack jokes. I like to tell some of the myths. And then we have all the telescopes. Our club members bring out our telescopes. They're not there for us. They are there for you to look through, to learn, to enjoy. So definitely come out to some of those events. A lot of activity from Cooper in the chat. Let's see here. Also, good job on 100 subs. Yep, I saw that I got 100 subs. I'm really excited about that. And Cooper's bringing his telescope. Excellent, excellent, excellent. Cool, cool, cool. All right, well, we got about 5 minutes left in the stream. I don't really know what to talk about in the last 5 minutes. There was actually one thing on my list I think I didn't talk about. There's two things. Why does the moon turn orange near the horizon? And belts of Venus and Earth's shadow, and those relate to each other, so I'll talk about them. Also, I didn't even think to put this on my list. Why does the moon turn red during an eclipse? These are all astronomy color topics. Let's talk about it. So, in addition to Rayleigh's scattering, remember I said the blue gets scattered, but the red not so much? Well, that gives the atmosphere a bit of like a filtering aspect, if you want to think of it that way. So what happens is, as light passes through Earth's atmosphere, it filters out the blue, and the red kind of gets through because the blue starts scattering everywhere, right? During a lunar eclipse, the only light that's hitting the surface of the moon has had to go around the Earth. So instead of coming down through the atmosphere like this, right? So you think the atmosphere is like this thick, right? The light just goes whoop, through that much atmosphere. But then take that across the Earth, and the light takes this path, right, across the surface, because it's coming around the edges. That is what turns that light red. The red light that you see, let me bring up a visual. Why am I not using visuals? I think as I'm trying to rush in these like last 3 minutes. Total lunar eclipse. All right. All right, so the reason why we get this reddish color, that reddish color that you are seeing is effectively the combined red light of all the sunrises and sunsets happening on the Earth at that time. That's what it really is. If you were on the moon during a total lunar eclipse looking at the Earth would block the sun and get a red ring around it, right? That's the light that's reaching the moon. So that's why the moon turns red during a lunar eclipse. And the reason why it looks orange near the horizon is the same effect. That the light that's reflecting off of the moon and then reaching your eye has come across the surface of the Earth and filtered down to this orangish color. The blues have scattered, and the orange is what's making it to your eye. Now, somebody, I'm sure, if I check the chat, making you homesick for Florida. I know, man. Somebody is gonna wonder, why does the moon look bigger near the horizon? The short version is that is just an optical illusion. If you hold up a ruler, or you use a dime to cover the moon, or you do something to measure the moon's size, it actually does not change. The difference is that it's an optical illusion. It seems bigger because it's going behind objects, and your brain realizes, oh, holy cow, that thing must be huge because it's behind those trees and still looks that big. When the moon is up above your head, you have no frame of reference, and your brain doesn't interpret it as being as big visually. But the truth is, if you measure it in both positions, no actual size change. And then lastly, I'm going to just bring up an image of the belts of Venus. This is going to be really fast to talk about, so it's a really cool thing to end. And it's very beautiful, and it's something that you can see for yourself any day if you have the right horizon line. Ooh, this picture shows it really well, and it actually shows the other phenomenon that goes with the belts of Venus. So let's talk about it. So remember how I said, right? The red light goes, the blue light gets sort of filtered out, blah, blah, blah. So this picture is taken with the sun setting behind the guy taking the picture. So we're looking at the opposite side of the sky from the sunset, right? So you get all the colors of the sunset behind him, but directly opposite the sunset, you get this blush pink rose kind of color right here. And this is called the belts of Venus, not to do with the planet Venus. Think the goddess, the Greek goddess, right? This is the girdle of Venus because it's pink and beautiful, right? We associate it with Venus. So that's what that is. That's that light coming through. But the belts of Venus has this interesting hard edge at the bottom of it, right? And depending on when you look at it and the conditions, sometimes this is more obvious, sometimes this is less obvious. What this is the sun is behind us. Oh, look at that. We even got the moon down there. What luck. The sun is behind us, right? Casting light, creating this effect, and the Earth itself casts a shadow on its own atmosphere. So what you're seeing is this pinkish light from the sun and then Earth's own shadow projected onto the little bit of sky you can see. That's actually, that bit of light is blocked by the Earth itself. Isn't that cool? That with the right conditions, you can see the Earth's own shadow. When I learned that, I thought that was really cool. It's not an astronomy thing per se, kind of astronomy related, really more of an atmospheric phenomenon. There's a whole bunch of those too we could talk about. Sundogs, the 22-degree halo around the moon, on cold, damp nights, that kind of thing. But this one is one of my favorites, the Belt of Venus and the Shadow of the Earth. I think it's really cool. We're 1 minute over, which is fine. I just wanted to talk about this. And with that, I will bid you guys all a wonderful night. I will remind you guys to get outside, look up, enjoy the beauty of our universe, and definitely tune in third Thursday next month and check us out. And yeah, man, you guys, I wish you guys all clear skies and a wonderful night.